just for the talks on the online to see. It is a great pleasure to present you Rafael Araujo. Rafael is currently an assistant professor at FGV Sao Paulo. He is a recent graduate for FGV Rio de Janeiro, and his research covers deforestation. He has extensively studied deforestation, determinants of deforestation in the Amazon, and I'd say he has, in his very short career, become one of the world leaders, experts in deforestation, in modeling, understanding the determinants and consequences of deforestation. So it's a great pleasure to have him. And Rafael, floor is yours.
Thank you, everyone, for being here. Thank you for the invitation. It's a pleasure to present my work. And the idea of this paper here is to try to bring a little of natural sciences into economics. It's hard to sell this kind of papers in economics, but let's see if you like it. And as I was explaining to Felipe, this is a picture from Sebastião Salgado. It's the best Brazil has to offer. You should check it out. Okay, so what is the idea of this paper here? The idea is that rainforests, so I'm talking about the Amazon and the Congo Basin and Southeast Asia. So these rainforests, which are highly dense, forests with a high density of trees, they create a lot of rainfall. And I'm going to explain how, but they create a lot of rainfall. And what is interesting is that this rainfall are going to affect the climate on a continental level. Rainfall is also going to affect temperature and other climate outcomes. And one implication of the fact that this forest creates a lot of rainfall is that if you have more deforestation, you'll have less rainfall and higher temperatures. And this has been known for decades. So this is the seminal paper by Enes Alati in the Amazon, in which he calculated that half of the rainfall in the Amazon is created by the Amazon itself. And around 30% of the rainfall in South America is created by the Amazon forest. So if we were to get rid of the Amazon forest, we would lose 30% of all the precipitation in South America. The problem here is that this has been largely ignored in economics and in a lot of different fields, and there are a lot of reasons for that. And in economics, like, we are trying to care more about what natural science is saying, but this is usually focused on this production, emissions, and temperature, climate change, in no sense. But the idea here is to bring more of natural sciences into economics. I'm going to try to convince you that we should do that economics has something to contribute here. But the idea is that to connect things across different fields. So the idea of the paper is to take what natural science is doing and connect with what we are doing in economics. It's to build a model that's taking what natural science is doing seriously. That's the main idea. So this is a picture of the Amazon. This is the Amazon River. This is the city of Manaus. But this is not actually one picture. This is take different pictures at different times and combine them to get a clear picture like that. Because if you were Superman flying over the Amazon, this is more likely what you would see. And this is during the winter, because during the summer, it's impossible to get a clear picture in the Amazon, because the Amazon is creating a lot of humidity that goes to the atmosphere, and then it gets transported, creating rainfall. So this is what creates the flying rivers. So this is the picture that I have to explain what the water cycle is to economists. So maybe most of the people here won't need that. Sorry, no problem. But just to get everyone on the same page, just try to explain the mechanism behind the model here. The idea of the water cycle is that you have the energy of the sun evaporating the water in the ocean, So this increases atmospheric humidity, and because of atmospheric transportation, this is transported into the continent, creating rainfall. The further you get into continental land, less rainfall you have because you are losing humidity, right? So the idea of the presence of the forest, like the Amazon forest, is that each tree is constantly capturing water from the soil, and through photosynthesis is recharging the atmospheric humidity, recycling the rainfall water. So in the presence of the Amazon, you have a higher level of total precipitation, but also it goes further into continental. So without the Amazon and with the Amazon. That's kind of the mechanism. That's what Enes Alachi discovered in the 70s. And then there is this idea, a really cool name for that, which is the flying rivers of now. That's the name of them. And this is more like what this pattern of atmospheric transportation looks like in the Amazon. So it comes from the ocean, it goes through the Amazon, and then it comes to the rest of South America. The Andes play a significant role here, like blocking the atmospheric transportation. That's why when I was flying to arrive here, I thought I was gonna die. You are flying over the Andes because there's a lot of turbulence because of these atmospheric variations. Okay, so the idea here is we know a lot about the causes of deforestation in the Amazon and in other forests, which is crops and cattle ranching. But deforestation is going to affect climate. Less rainfall, higher temperatures, and this is going to affect agricultural productivity because we have less water and temperatures are higher. But in the literature so far, we are not talking to each other here. So there is a large literature only looking at how agriculture is going to affect deforestation, but it's not accounting for the full cycle. I am guilty of that thing. There's another literature, and then outside and within economics, looking at how deforestation is going to affect climate. And most of this is from the natural sciences since the 70s, so decades and decades of research showing how this mechanism works. And then there is a huge literature both outside of economics and within economics explaining how climate is going to affect agriculture. So you have like higher temperatures is going to affect productivity of corn and soybeans and cotton, and you have different ways of estimating these impacts. So the idea of this model is just to go full circle here. Look at these three components in one single consistent model that we can estimate and simulate the results. So this is my attempt of bringing natural sciences to economics. Okay, so I'm just going to present the model and then an application that for the Amazon rainforest that we can use the model. Okay, so the first part of the model is how deforestation is going to affect climate. Okay, and this is it's a system of different equations, but I can explain that with this picture here. It's pretty straightforward. So this is an illustration of the Amazon. We have the ocean, we have the forest in green, and we have deforestation in yellow. Now suppose I'm going to understand how this land use configuration here is going to affect rainfall in this white pixel, which could be a farm, could be a hydropower plant, for example, anything that is of interest. So the idea here is that I have this trajectory of atmospheric transportation, which is just how the atmosphere moves around. And the idea is that I'm just going to count the amount of pixels of forest upwind of this white pixel. So for example, in this picture here, I'm going to have 14 pixels of forest. Okay. And then on the second picture, where I have the same land use configuration, but a different atmospheric trajectory because they vary year to year, I'm going to have a different count of forest. So for example, here I'm going to have 10 pixels of forest. Okay, I can have that this pixel here is farther away than this pixel here, so I can just have different rates for where you are from me. So you are going to affect me more than it's going to affect me. But the idea of the model is just to connect climate outcomes with this measure of upwind exposure to the forest. So what is the idea? The idea is that, okay, I have cloud formation in the ocean, and this is traveling the continent. The more pixels of forest this cloud is flying over, the more recharging of the humidity it's going to be exposed. So more rainfall, it's going to have more humidity to deliver as rainfall. But if I don't have forest, it's just losing humidity along the way without this recharging process. So the idea is the more exposed this cloud is to the forest, the more humidity it will have to deliver as rainfall. So that's the idea of the model. And this is surprisingly simple and it works, but it was only in 2010 in a Nature paper that someone thought about testing this with observational data. Before that, it was all like field work and simulation models. So I have one model that comes from first principles, and then I calibrate the parameters and simulate them. So it was only in 2010 that someone thought about, like, let's estimate this kind of model. So this is the climate model. So this is what I brought from natural sciences. And the idea is to put that in an economic setting so that we can estimate and we can have confidence intervals. Okay, so this now is what I'm bringing from economics. How we are going to model how people are going to react to different climates. So this is my problem with what people do in natural sciences, that most of the papers, there is no adaptation. Like I'm growing soybeans, and then I'm having like less rainfall or higher temperatures, and I just expect people to keep growing soybeans. And so the idea here is to model adaptation, model how people are going to react, and what are the mechanisms for people to react to a change in the climate. So the idea here is just to think about profits. So each farmer in the Amazon, they have a range of profits that they can choose from. So for example, I'm going to grow soybeans. I'm going to use my land for cattle ranching. I'm going to grow soybeans and corn in the same agricultural year, which is something that's really hard to do. And each of these options is going to give you a different profit. That's going to depend on a lot of things. Transportation cost, price of soybeans, price of fertilizers, wages, and it's going to depend on climate as well. But this is just a function that, given the economy, this is going to give the profit for each choice that you have. But the idea here is that in economics, people take this as given. The idea is to take the model from natural sciences and put that in this place here. So climate is not given. Climate is going to depend on what other people are doing. So my agricultural productivity is going to depend whether Felipe is going to deforest or not, whether you are going to deforest or not. And your decision of what you are going to do depends on whether I'm going to deforest my land or not. And this is the mathematical challenge here. Okay, so I have this function of profits that's going to depend on transportation costs, climate, etc., etc. And then this is just like a mathematical necessity. I have some different choices. You can just think of soybeans, cattle ranching, or not deforested. Keep my plot of land as forest. And so different choices are going to give me different profits. And then I have to have some assumptions on idiosyncratic costs. And then I can write down a probability of not deforested. Okay. And this was like, for me, this was it seems ugly, but for me, this was kind of the big leap that I took to write this paper. Because the idea was that bringing the climate model into economics was mathematically very hard, because we have all of these interactions. And it's hard to model these interactions. But the idea is, if we use this kind of model that we call discrete choice model, so I have a discrete set of choices to choose from, soybeans, sterile, forest, I can write down this probability that I'm going to observe a person deforesting their plot of land. And this probability is going to depend on the probability of everybody. So this is the mathematical tool that allows me to write down the model. So it's a vector of probabilities that depends on a vector of probabilities. So that's the idea that was necessary to bring natural sciences into economics, into the language of economics. So what this means is that this probability is going to depend on climate, and the climate is going to depend on the probability of everybody else. So if you are deforesting, I can map this to my decision, and my decision is going to be mapped on your decision. And so the idea here is that mathematically, this is a fixed point. We can talk more about this if one wants to know the details. But that's the idea. The probability that I am going to deforest is going to depend on the climate, which depends on the probability that everyone is going to do. So mathematically, this is it. Like, probability that I'm going to deforest depends on the decision of everybody else, a vector of everybody's decision. And then I just find the equilibrium of this one. Okay, so the problem that, like, alternative ways of thinking about that is what I was talking earlier. Like, I want people to react. I want you to change your probability of deforestation given my probability of deforestation. I don't want mechanical agents in my economy. Like, I'm seeing that my neighbor is deforesting, this is going to affect my climate, but I keep doing the same thing. That's the idea that this model is trying to capture. Okay, and then we have this model in place. I can map deforestation to deforestation, and then I have this application here. So the application of the model is on the Amazon rainforest, this place here. And the idea is that I'm going to look specifically at the Brazilian state of Mato Grosso. Mato Grosso produces around 10% of all the soybeans that are consumed globally, so it's a lot of soybeans. And this is produced here in the center of the state of Mato Grosso, but it's surrounded by protected areas. Protected areas can be only protected areas in the sense of conservation units, or they can be indigenous territories. So it's territories that are protected from deforestation and from mining, etc. And it's allowed only indigenous activity there. You're right, because we know that a lot of things are happening there, right? Particularly after the Bolsonaro administration. So the idea here is, okay, I have a bunch of people producing soybeans in the center of the state, but there is a constant push to deforest more land, to walk back the protection status of a lot of indigenous territories, of a lot of different conservation units in Brazil. But what we learned from the model is that, okay, but if I'm going to deforest a protected area, I'm going to have a worse climate in the rest of the state. So I'm going to produce less. So is it worth doing that? Who are the winners and losers of this type of policy? This is what I'm trying to answer with this model. Okay. And so this is the indigenous territory of the Xingu. It's a lot of different people that live in the Xingu. And so the idea is that I'm going to estimate the model of how people make decisions using data from private properties in Mato Grosso. And then I'm going to apply these parameters from the model to the indigenous territories of the Xingu. So effectively rolling back the protection status of the Xingu. But the idea is that if we had a new political system that allowed people to deforest here, what would happen to the rest of the production, agricultural production in Mato Grosso? That's the idea. That's the counterfactual. That's the exercise that I'm going to use my model. Okay, so why the Xingu? I don't know if you can see here, but like you can spot the frontier of the Xingu from the picture, right? So this is all protected. This is part of the Xingu, and these are all farms, like the foresting around the Xingu. So the idea is what would happen if we were to allow more deforestation in this area here. And then this is, as I was discussing with Felipe, this is my attempt to, think this is not necessary for this audience, but I've been having a really hard time explaining to people how important it is to study indigenous territories and indigenous rights. And this slide is just my attempt to say that it is important. There is a lot of threats on this territory, and these people, they suffered a lot, and so just trying to bring this dimension into my what I have here. Okay, so then how do we operate these models? So we need a lot of different elements. The first one is a model of atmospheric trajectories, a model of atmospheric circulation, and this is from natural sciences. So we have like yearly data on wind. So it's for each month, there is a 3D matrix that gives me the wind velocity and direction. And then I can use that to build this back trajectories of atmospheric transportation. So it's a model of atmospheric circulation. Okay. So it allows me to track cloud formation from the ocean to any place that I want to track it. So this comes from Copernicus, and we have data from 1985 to 2018. And then we have this really nice data from Map Biomas, which is also from 1985. Which classifies for each pixel, South America, each pixel 30 meters by 30 meters, its land use. And there is a lot of different categories, but I'm just going to use like forest or not forest to build this upwind forest exposure. How many pixels of forest there is upwind of a place. Okay, and then this is more for like trying to translate what natural science is doing to the economics language. And the idea here is that we want to estimate this model. Why do we want to estimate this? Why don't we calibrate the model or use a calibrated model? Because in economics, we like to discuss what we call identification, but also because we want to do inference. Like we want to have an estimate and we want to have a standard deviation for this estimate. So the idea here is just to build these back trajectories and then overlap the back trajectories with the Map Biomas data. And then we will have what I call the upwind forest, which is just the count of pixels, upwind of a place, and rainfall or temperature in this place. So it's rainfall in the white pixel regressed on upwind forest. So rainfall regressed on the count of forest pixels, right? So this is the climate model. It's just a linear regression, but this is really powerful because this model here, it recovers a lot of the statistics that were generated in natural sciences by field studies and these calibrated models as well. So a linear model here it seems to be enough to capture all of the complexities that we want to capture in this model. If anyone wants to talk more about identification, I'm happy to do so, but this is more like a concern from economics. And then from the other side, so this is the climate model for the land use model, for the discrete choice model of land use. We are going to use this very rich data that classifies pixels in Mato Grosso. And I'm not using Map Biomas here, I'm using this data because this data, they classify what is called double cropping. So double cropping is when you have soybeans followed by corn in the same agricultural year, because something that's really hard to pull off. It requires a lot of technology and management from the farmer. And as you can see, this in purple here, this is where there is double cropping in Mato Grosso. So you can see that there's a lot of double cropping here. Xingu is here. And then there is not a lot of double cropping here. So there is this theory that without the Xingu, you cannot have double cropping in Mato Grosso. So the Xingu is kind of protecting the double cropping in Mato Grosso. And this is what allowed Mato Grosso to be this very important agricultural hub nowadays, having this double cropping. Okay. So the idea here is to use this model with this data, with a lot of other data that I have from my other papers, like transportation costs. So how much does it cost to transport soybeans from this pixel to an international port? That's what they do, just exporting soybeans. I also have data on soil and slope and all kinds of variables that we use to estimate the economic model. So what is the probability that someone is going to deforest as a function of all of these variables? So the idea here is, let's just go back here. So the idea here is, this is from natural sciences, like upwind forest affecting rainfall or temperature. This is from natural science. And this is from economics. Rainfall and temperature affecting the probability of deforestation. Separately, there is no contribution here. Like from natural science, they've been doing that for decades. And from economics, we've been doing that for decades as well. But the idea now is, okay, now I use the theoretical model to connect these two parts. So climate here is going to come from the climate model, but the climate model is going to come from the economic model. And that's the contribution here of the paper. Okay, so I've been table with the results. This is the results from the climate model. The idea here, a lot of numbers, but just to say that, so this is the regression of precipitation and temperature on upwind forest, the exposure of pixels of forest. And so what I recover from this is that if we increase upwind forest, so I increase the exposure to the forest, in one standard deviation, I have 10% more of rainfall. So I have one place here, and I'm going to have more forest along the back trajectory. If I increase this upwind forest by one standard deviation, in this place, I'm going to have 10% more of rainfall. So it's a sizable effect here. And this is what we expected, what we know from natural sciences. Half of the rainfall in the Amazon comes from the Amazon itself. But what the model here allows me to do is to build any kind of counterfactor that I want. I want to deforest some plots of land. What is the impact of that on climate? Right. I also have the impact on upwind forest on temperature. So the more forest I have, upwind of allocation, I will have milder temperatures. So one standard deviation is going to decrease temperatures by 0.1 degrees Celsius. It's also a lot of, it's a sizable effect as well. And what we like in economics, but it's not so important outside of economics, that we really care about the numbers here, the standard deviations to do inference. But then, like, this is physics. And in economics, we are used to like really dirty data that always gives us some crazy high standard deviations. But here you can see that it's really small because it's physics, like it works. It's not like sometimes we do in economics. So people always, in economics, they ask me, are you taking this, like, are these standard deviations correct? And I say, yes, it's correct, it's physics, it just works. And this is the part from economics. So this is a regression on upwind forest on rainfall and temperature. And this is the other side of the coin. So it's climate on land use decisions. And so what I have here is a regression of upwind forest on the probabilities of choosing to use your land as your plot of land as for pasture grazing as cattle ranching, or double cropping, so soybeans and corn, or only soybeans. And the idea here is that I find almost no significant effect of changing the climate on our decision of deforesting to use that as cattle ranching. And that's because cattle is very resilient to changes in climate. And that's because cattle in the Amazon is a very low productivity activity. You have one cattle head per hectare. But it's not like it's not nature that is the constraint for you to have a more profitable activity there. There are credit constraints, there are property rights problems, and all kinds of things that are going to constrain the activity of cattle ranching. So cattle ranching is not going to be affected, at least at this level of productivity in the Amazon, by a change in climate. So that's the lesson here. But on the other side, we have that double cropping, so soybeans and corn, and single cropping, so only soybeans, is going to be heavily affected by changes in climate. So if I have less rainfall, I lose my capacity to produce, to choose double cropping as my land use activity. So what is the economic side of this is that, okay, I'm having less rainfall, higher temperatures, my productivity of soybeans is decreasing, but I'm not gonna keep producing soybeans. I'm gonna do something else. I'm going to go to pasture. And this can explain in part in some regions in Amazon where we see the switch from crops to pasture. And this is hard to rationalize without this because you can see that pasture is less profitable on the average, but this kind of explains why we see this in some places in the Amazon. Changing climate is going to affect your productivity, is going to affect your decisions. So this is the idea. This is what the model allows me to do. So people are deforesting, it's affecting my climate, and it's affecting my land use decision. My land use decision is going to affect the climate of someone else, and it's going to affect their decision, it's going to affect the climate of someone else, and their decision, and so on and so on. Okay, so going back to the exercise, I estimated the model, I have the parameters that I'm going to have. And now I go to the application. So the idea was that these parameters here, it comes from data, the map that I showed before, data from private properties in Mato Grosso. So what happens if I were to transform the Xingu indigenous territory in private property? So I'm going to allow people to deforest there. I'm going to have more land to use that for cattle ranching or for soybeans, but this is going to impact climate on the other regions. This is going to generate winners and losers. I'm going to have winners, whoever gets to get land from the Xingu, because they are going to produce more. And I'm going to have losers because people outside of the Xingu is going to have a worse climate. Okay, so this is what would happen. Okay, so if I were to allow deforestation in the Xingu, almost half of the Xingu would disappear. And this is a static model that have like building new roads through the Xingu, and this would affect transportation costs and land use decisions. But this is like, as the economy in Brazil is today, if I were to allow deforestation in the Xingu, half of the Xingu would be deforested, giving place to soybeans and cattle ranching. So I'm going to increase production, agricultural production, right? But then this is going to affect climate in the rest of the state of Mato Grosso. So I'm going to decrease rainfall in some places, and I'm going to increase temperature in the same places. So this is more or less 16% of the historical average of rainfall. So these places here could lose as much as 16% of the historical average of rainfall. And these places here would see an increase in temperature of almost 0.4 degrees Celsius. So it's a lot. And this matches a lot of the numbers that we have from local exposure to deforestation on the increase. So this is yet not a map of winners and losers, because what is going to determine winners and losers is the interaction of this changing climate with the location of where people are producing soybeans and corn. And this is what we see. Okay, so the idea is I'm going to deforest the Xingu. I'm going to change the climate of a lot of different people, and these different people are going to change their land uses. Remember that in the center of the state is where the most productive agricultural frontier is, that they produce a lot of double cropping. And they are the ones that are going to stop choosing agricultural activities. So this is the probability that they are going to, in the model, they are going to abandon the land. They are not going to keep producing cattle, using the land for cattle ranching or soybeans or corn. So some regions, almost more than 10% of the pixels, more than 10% of the land would not be used to agricultural productivity. That is, there is a proportion of land that we're producing soybeans and corn, but because of the deforestation in the Xingu, because of a worse climate, they are not going to produce agricultural goods anymore. And this is the region here. And this, in the model, I can translate each decision to a profit, so to a land value. And this is what would happen to land value. So in the center of the state of Mato Grosso, a lot of regions would lose more than 20% of their land value. And so this is kind of the main result, because the idea here is that these are the losers and the winners are within Xingu. I'm going to have more land to produce agricultural goods in the Xingu, but I'm going to have a worse productivity outside of the Xingu. And because of the patterns of atmospheric transportation, because the Xingu is right here next to the center of the state is going to be very affected by deforestation in the Xingu. So some pixels would lose as much as 20% of their land value. So I get winners and losers. And so the idea here, my main idea with this paper is to kind of try to change a little the narrative of conservation in the Amazon. Because right now we try to push this idea a lot, very heavily, that we need to protect the Amazon because of emissions and global climate change. But this is really hard to sell to Brazilians, right? Like, we should care about emissions. China is emitting a lot in rich countries, and if you take the historical emissions, etc. But this is a different narrative. Like, there is a concern for Brazilians itself to care about protecting the Amazon. There is a reason for farmers, which are the ones that are like have been pushing for more deforestation in the Amazon. There is a reason for them to want to protect the Amazon, right? So this is my attempt to shift the narrative a little, to stop focusing only on emissions and try to focus on what is going to happen with the Brazilian economy if we allow more deforestation, right? Okay, and this is the last picture, just showing that what I was explaining, that okay, these people here, they are losing agricultural productivity, but most of them are going to shift to cattle ranching, because cattle ranching is not going to be affected. The productivity is not going to be affected by the changing climate. So the idea is that if I have if I had a mechanical model where people cannot change their land use, this would be way worse. So this is what a lot of papers that I've seen in natural sciences, they do, like they just take a mechanical agent and the agent does not react. But the idea here is that this is a distribution of land value. It's normalized, but this is a distribution of land value. In dark gray here is the distribution without adaptation. So people are doing the same thing, like the climate is changing and people are doing the same thing. So there is this head tail here that tells me that adaptation is important. So the light gray area, the light gray histogram, is the histogram with adaptation. So I can move land values to the right if I have adaptation. So that's the what we gain from having an economics model. Okay, so just to conclude, so the idea is to show that we should take into account that land use decisions are going to affect climate. So what we've been doing in economics is just ignoring that. Like if we deforest the Xingu, we are going to have more land, more agricultural production, and that's it. But what this map shows is that this is going to have consequences for a lot of people. So we should take into account the climate model here. And there's a change in narrative that I think is important, and this goes beyond agricultural production. I have another paper where I look at the impact of deforestation on hydropower generation in Brazil, because 60% of electricity generation in Brazil comes from hydropower. The number we have is that because of deforestation, as it is today, the energy sector in Brazil, they lose $700 million per year because of they're not producing as much energy as they could. And there's also a necessity of protecting the Amazon for the stability of the forest itself. But what is most important is that the climate model allows us to map winners and losers. So it's not that we should be keeping pushing for more deforestation, like farmers should be keeping pushing for more deforestation, so we have more agricultural production. This is not true in this model. We are going to have winners and losers.